Here is the second or oscillator section of this laboratory. What we have built here is the phase shift oscillator presented in the TI application note as the Bubba oscillator. What's unique about this oscillator is it uses 4 phase shift networks, which are RC filters. We can see 1, 2, 3, and 4 capacitors and the resistors associated with them to provide 180 degrees phase shift, which along with the negative feedback amplifier provide 360 degrees total phase shift around the from output to input on the oscillator. This is the so-called Barkhausen criterion, where on a negative feedback amplifier you need a gain of 1 and a phase shift of 180 degrees in order to satisfy the oscillation requirement. When you build this circuit, you need to make 2 adjustments. One on from this potentiometer, which adjusts the DC voltage into the first op amp. This is a bias voltage that allows you to kind of get the amplifier and oscillator started. And the second is the gain of the first stage, which is determined by this 5 meg potentiometer. This potentiometer here, since it's not used as a resistance but as a voltage divider, it simply is connected between positive and negative supply voltages so that the input voltage can be some value that optimizes the oscillation process. Here are the end results. As you can see, we get a very nice sine wave oscillation from this unit. To compare this signal to another regular oscillator to see its quality and frequency stability, once you have the circuit working and oscillating, compare it to a signal out of your arbitrary waveform generator. In this case, I'm using a signal of 1700 and actually 1729.8 hertz. I've already tested this one, and we'll compare it to the oscillator. The oscillator itself is oscillating at 1730 hertz. So we'll compare the two and look at them, and we see the difference being displayed, and you can see that the two signals are very close in frequency, which allows us to indicate which do a direct comparison with the two signals. There's a little phase difference which we see as the waveform oscillator moving slightly in to the left. I can adjust the frequency slightly to make the two signals stand still. And as you see here, I've made a small adjustment to get the two waves to almost be identical in terms of phase. And once these two waves are standing completely still, we have the new frequency of that oscillation. In this case, 1729.56 hertz. Just a little bit different. If I adjust too much, you'll see that the wave will start to move the other direction, meaning its phase shift is changing. Now, the signal we're adjusting is an arbitrary waveform generator, which is actually a very stable signal. The frequency of our oscillator is actually changing slightly, but since we're triggered on that signal, it is the one that appears to stand still. So now we're at 1729.46. This is a very good sinusoidal oscillator. As you can tell, the two signals are almost identical in terms of display. I'll move this to AC so we can compare the two a little more directly, and we will quite easily be able to adjust these two signals to almost be identical. In magnitude and in shape, as the phase slightly changes, you can see. So that is an excellent sine wave oscillator. The only difficulty is this is a very low frequency, not high enough for RF applications. Now, once you have this signal, this oscillator built, there's only a few measurements that you really need to look at. We will look at each part of the phase shift oscillator. So we'll change our signal measurement from the ARB generator now to a couple different points in the circuit. Okay, so now we are going to be showing the difference between the oscillator signal before and after the first negative feedback amplifier, actually the only negative feedback amplifier. And we see the two signals shown here, and the phase is indicated at 187.8 degrees. Okay, theoretically should be 180 degrees, but on this measurement it's 187.8. So 187.8 degrees between the two. Now the two signal levels are roughly the same. One is about 15 volts peak to peak, the sinusoidal oscillation, and the negative phase shift, which is a little distorted. You can see it's a little flat topped in a couple areas, such as this and this. Now we will move to a next point down the line, which should represent a phase shift of 180 plus 45 degrees, which would be 225 degrees. That is one point just beyond. And now we see the signal change. Now the indication is a minus 130 degrees of phase shift. You must add that value to 360. So minus 130 plus 360 is 230 degrees. And that is the phase difference between the two signals. You'll notice that the signal decreased somewhat in value because it went through a phase shift of oscillator, or the 45 degrees, so it dropped by 0.7 degree magnitude. We'll move to the next point, and we should expect to see another 45 degrees worth of phase shift. So that's the next section of the phase shift oscillator. And we see now it is minus 86 degrees of phase shift. So minus 86 plus 360, that's very close to minus 90 plus 360 would be 270. And you'll notice it dropped again, 0.707 from the RC phase shift. The last signal then, we should see a 45 degrees phase shift between the two. And indeed, we see minus 44 degrees between the two. So the phase shift oscillator works by 180 degrees from the first amplifier, the negative feedback amplifier, then 45 degrees for each of the next four stages. So we get 180, 225, 270, 315 degrees of phase shift, and then the loop is completed. An interesting part of the phase shift oscillator is to take a look at the startup signal associated with the oscillation, To do that, we will monitor the output of the completion of the loop, which is RG in the diagram. All right, so now we are ready to demonstrate the startup sequence for the oscillator. I have turned off the power to the power supplies, so the op amps are not working. The oscillator will not work without power. And I've done some special triggering in this case. I am going to set up the scope for single sweep trigger. Okay, so we'll look at the signal first, and I'll show you then how we set it up. Now, in this case, we can see the oscillator startup process. This is the output, or the input to the negative feedback amplifier. So we see that voltage first goes positive, and then it starts the oscillation process. All oscillators start as amplifiers, so we see the amplification, but it's not a stable amplification because of the positive feedback, and so it goes positive, and then the oscillation starts, and eventually the oscillation builds up, limited by the power supply, and then it stabilizes. So that's the oscillator startup process. The oscillators don't start up, just the operating frequency. It takes a little while for the signal to build up. But once it's built up, we get a very stable oscillation as we have seen before. Frequency has to be set at where the loop phase shift is 180 degrees for the Barkhausen criterion, or a total of 360 degrees. And that's the process. It's not required for you to record this data, but it's something useful to understand that the oscillator process is a dynamic process, at least on the startup. As a comparison, I built this Bubba oscillator with both 4 single op amps, 741 style, and here is with an LM324, which is a quad op amp. I use the same R and C values. 1, 2, 3, 4 capacitors are involved in the feedback network, and the end result is we can see two oscillations that are almost identical in terms of magnitude and frequency. Of course, the frequency is determined by the RC values, and since I use the same RC values here as I did here, we would expect the same frequency. Both are incredibly stable with respect to each other because they have to be the same frequency. There's a small phase difference because each oscillator starts its oscillation process at a different point in time. But as long as their frequency is essentially the same, we can tell that there is no drifting, or the frequency is determined by the RC time constant associated with each one of the stages. So this circuit can be built with a quad op amp, 7324, or 4 single op amps. It's your choice. The little smaller circuit here. Again, we have the 5 meg ohm pot for the gain, and the 10k ohm pot, which establishes the voltage bias associated with the first amplifier to get the oscillation started. The optional oscillator to be built is a higher frequency sinusoidal oscillator. In this case, we're using the circuit shown in the handout. This is a crystal oscillator. So we have taken our color burst crystal over here. It's a 2-stage oscillator in that there's the first stage is the crystal oscillator transistor. That's the oscillator part of the circuit, and then there's a buffer amplifier on the output. And we're looking at the output of the signal. Since this is a crystal oscillator based system, it is based upon the crystal frequency, which is our color burst 3.57 megahertz, and we see a value of 3.6 megahertz on the oscillation. This signal is not quite as sinusoidal as the phase shift oscillator. A little distortion in the sine wave there, but is certainly close enough in terms of a signal magnitude or frequency. And we have some adjustment on the signal level also. Looks, we can adjust it to be a pretty good size signal by adjusting the potentiometer on the output. Oscillator does a little better in terms of performance at lower frequencies, and we can do a little averaging there, and we see our sinusoidal oscillation at the 3.6 megahertz, but it's the crystal frequency. One interesting thing about crystal oscillators is, since the frequency is determined by the crystal, we can change the crystal and change the oscillator. So we'll show that part. So in this case, I've changed my crystal to now 2 megahertz. And if I look at the signal on the scope, I see a 2 megahertz signal. So a crystal-based oscillator, since the frequency determining element is the crystal, the amplifier doesn't need to change. I had to adjust the output level a little bit to get a stable signal, but all I have to do is design my amplifier, change my crystal, and I change my frequency. In the old days, radios would have multiple crystals, and they could serve as multiple channels. That has changed in the recent past, because now we use a single crystal oscillator and use a phase lock loop and synthesizer to change the frequency. So we only need one stable oscillator, and that is good enough.